Okay, so we went over a bunch of stuff on the last video. I mean, it seems complicated, but just just to kind of go over the highlights, what you really have got to know is you got to know how light is given off in a firework, something like that. We add energy, electrons move, they give the energy off. So this concept here in this area, that's pretty important. Okay, so that's pretty important stuff to know. Okay, now the second thing, and this does need to be memorized, is that if I land somewhere, what kind of energy is given off? So if I land in the n equals 1, it's UV. N equals 2, it's visible, etc. This, very important. Okay, so things that could show up on a test. So here's a example, super duper simple. It says, which transition, zoom in a bit. It says, which transition releases a photon with the shortest wavelength? Okay, they do this a lot. So right away, we need to understand how does wavelength relate to energy, etc. Okay, so we want to remember that wavelength. So I want to remember that wavelength is going to have an inverse relationship with energy. Okay, so wavelength and frequency slash energy, those are wavelengths and frequency slash energy. These are opposites. All right, wavelength and we are these are the same thing. Frequency slash energy. These things are inversely related, meaning if one goes up, the other is going to go down. We got an inverse relationship. Okay, that's really important to know because you can't answer this question if you don't understand that. So you have to know this. This is a definite test concept. And so we're going to come over here and we're going to say to ourselves, okay, short wavelength. So I'm going to think to myself, short wavelength is also the same as a long or a high energy. So we're going to go in the opposite directions. So I'm saying to myself, okay, that's the same thing. So what are they really asking me here in this question? They're asking me which of these, A, B, C, or D, is going to give me the high energy. Okay. And so, which of these is going to give us the high energy? And so we're trying to figure that out, right? Which of these is going to give us the most energy? Because I understand this relationship is opposite. Okay. So we think about that and we're like, okay, we got this. Okay. So now which of these transitions gives you the most energy? Well, it's so first of all, you only release energy if you're going down. Okay, so 4 to 1, yes. 3 to 2, yes. 4 to 3, yes. 5 to 2. Okay, those all release energy. Okay, but what I want to show you is that n equals 1 to n equals 5, that doesn't release energy. That instead is going to absorb. So you got to be careful because they could ask you a tricky thing like that. So back to our choices. The most energy is associated with which of these transitions? Well, it's really very straightforward. Anything associated with 1 gives off the most energy. The only one that has a 1 is A. So it's the only possible answer because A goes to level 1. Level 1, anything that has a level 1 in it is going to have more energy. And so the answer is A. And the answer is because it has energy because of n equals 1, which we know that is the most energy. Anything involving the first energy level right next to the nucleus is the most energy. Okay, so you want to remember that n equals 1 equals the most energy. So you've got to remember that. Makes this a pretty quick, pretty easy problem. Okay, now Maybe they give it to us in a slightly different way, and we have to navigate it, but we're always going to be basically doing the same thing. So if we slide down here, I could give you another example. So do the same thing. Let's try and figure this out. Which one of these has the most? So we'll go n equals 3 to n equals 1. We'll go n equals 2 to n equals 6. We'll go n equals 1 to n equals 2. And we'll go n equals 2 to n equals 3. Okay, so 3 choices, A, B, C, and D. And so which one of these, again, is going to have the most energy associated with it? We'll do the same question. Well, let's go through it. The first one has a 1, which is good. We're looking for the 1. There's a 1. There's a 1. Okay, so those are good. But here's the problem. 3 to 1 versus 1 to 2. Well, this is the answer because we're coming back down to the 1, and that's a lot of energy. This is not the answer because this one is absorbing energy. So that's actually not giving off anything. And then this one is a 2 to a 6, which is a lot, but it doesn't have the 1. And it's also going in the wrong direction. We're going up, right? So this one is also absorbing. And then this one, 2 to 3, okay, that's another one that is absorbing. So you can look at all of these and just get eliminated because they all absorb, right? So anyway, something to think about. I think that that's pretty standard, straightforward stuff. So, all right, now we get into electron configurations. And electron configurations are not difficult. But what electron configurations are is that they are different in this course because we lied to you about some things last year. We sugarcoated it for you. We took some shortcuts, and this year we're going to have to go back and fix some of those mistakes. And so you're going to have to learn about exceptions. You're going to have to learn about things that don't follow all the rules, but it's still very similar to last year. So let's kind of do a few small things here. I've got a little bit of time left on this video. So let's look at the electron arrangement. And so when we talk about electron arrangement, we're talking about where the electron's at around the nucleus. And so they're going to be in layers. So that's S, P, D, and F block. And we talked about those last year. So if you look here, you've got the S block is these first two. And then, of course, it includes helium over there. The D block is in the middle. The P block is over here on the right. And then the F block is down here at the bottom. Okay, maybe not the best color. Down here at the bottom. Do need to memorize those because knowing where those is at is the key to solving all your configuration problems. Okay, so let's slide up here. Spin, orbital, Pauli exclusion principle. So we got some definitions to write down. So spin, hopefully I'm writing some things down that you're not totally like, I've never even seen that before. So last year you did stuff like this. Drew a box and did some box and arrow notation like this. And then you put an arrow up and an arrow down. And so that's representing spin. So we always had arrows going in opposite directions. And that's because electrons don't really like each other. And so what we want to write down for spin is we want to write down that electrons are going to spin in opposite directions. So they're going to spin in opposite directions. And then we modeled that with arrows. We model with arrows. So basically like one up, one down. So like that's the kind of thing we did last year to say, hey, this is showing that these electrons are going in opposite directions. And so we use the arrows as the electrons. So orbitals, what the heck is an orbital? An orbital is, well, we represent them with a box. So we would represent the orbitals with a box. But what the box represents, this is a space that can hold 2 electrons. And so remember, this is a 3-dimensional item, right? Like it's layers upon layers of electrons in a 3-dimensional item. It's not flat. So we're trying to model that with something that's in 2 dimensions. So we use a box, but this is a space that can hold 2 electrons. The electrons don't like each other, so they tend to spin away from each other. So that's why they're in these layers. And then we get down to some rules. Pauli exclusion principle basically talks about modeling. And so the Pauli exclusion principle says this. It says that an orbital can hold 2 electrons with opposite spin. So it says an orbital can hold 2 electrons with opposite spin. Well, how do we model that? Once again, we modeled that with a box. There's your orbital. And in that orbital, we put an arrow up and an arrow down. Okay. All right. See where we're at. Now we can go through a few more definitional items. S, P, D, and F. And so these are going to be the blocks on the periodic table. And so they have orbitals and they have electrons. So S is going to have, so if we think of it this way, we're going to go, we'll write down orbitals / electrons. Okay. So S has 1 orbital and it holds 2 electrons. P has 3 orbitals and it's going to hold 6 electrons. D is 5 and 10. And F is 7 and 14. So how do you know this? Just count the spaces and then that's the orbital, or count the spaces and divide by 2 for the orbitals, or just count the spaces and that's your electrons. So for example, so this is a space on your periodic table, just like that. So if we zoom in on that, and I look over here at the P block, well, let's say you can't remember this. Well, just do this. How many electrons? Okay, well, this is an electron. Get a different color that actually shows up. So this is an electron. This is an electron. Every box is an electron. So 1, 2, 3, 4, 5, 6. I don't have to memorize that. I could just count. Look at the D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 electrons. Okay. S, 1, 2. Okay. Now, if you need to figure out the orbitals, just take your electrons and divide it by 2. So for the D, I would just think to myself, okay, I just counted that there's 10 electrons. I'm going to divide that by 2. That's going to be 5 orbitals. Okay, so don't make this harder than it is, because it's really not that hard. Okay, let's finish up with a couple of shapes here. The S is often called a spherical shape. Well, that's because it's round. So if you look here at my picture, I've given an example of just a spherical shape, right? So that's the S. And the dumbbell is the next one. And so it's 3 pieces, 1, 2, 3, the 3 axes, X, Y, and Z. And so they end up kind of layering in on top of each other. And so you